thank you. Thanks everyone for coming back to the fourth lecture on quantum recursive programming. And today we will continue to study some examples that can be written as quantum recursive programs. And we will also start to talk about the implementation of quantum recursive programs. So let's recall the syntax for the language RQC++ for describing quantum recursive programs, and the syntax of RQC++. So here I will just write out the full syntax. First, we have a set of procedure declarations. So this is typically the program. So we have a set of procedure declaration U1. And we have this statement has of the following forms. First, we have the skip, classical assignment, and the classical if then else statement. Then unitary gate. Here we have sequential composition. Unitary gate. QIF statement. Local blocks, procedure call, and procedure call. Okay, so that's the syntax of RQC++ we've introduced the last time. So remember, the recursion is combination of the quantum recursion is a combination of these two features. First is quantum control flows. And the second is recursive procedure calls. So that's the overall ideas of quantum recursion, and in the syntax, this quantum if statement is the only guard for the quantum control flows. And for the recursive procedure call, it's like the classical case. We have these procedure calls with some classical actual parameters, and we also have these procedure declaration which declares a procedure with some formal parameters. And the overall program will be denoted by this curly P, which is just a set of procedure declaration. Okay, so let's continue to some of the examples. So last time I've talked about the examples including the classical recursion, like the GHZ state generation, and a quantum recursion example, the multi-control gate. And I also talked another more natural quantum recursive algorithm for generating the DT state. And today we will cover 3 more examples. First, the first example is a quantum Fourier transform, which is very fundamental building block for the short algorithms for factoring integers. Quantum Fourier transform. And I will also give you an example of circuit implementation of quantum random access memory. So this is its shorthand is QRAM, quantum random access memory. And finally, I will give you an example of quantum multiplexer. And this example will also be a motivation for the efficient implementation of quantum recursive program. So that's today's example, multiplexer. Okay, great. So first example today is QFT, quantum Fourier transform. What is QFT? It's a quantum version of the classical discrete Fourier transform. So remember, let's just write out its definition. So QFT with a parameter n, it's right here, parameter n. Now here n represents the number of qubits that this QFT acts on. It can be defined by a unitary mapping, which maps J to, here is the normalizing factor, 2 to the n, sum over k equals to 0 to 2 to the n minus 1, then e to the minus 2 pi j k over 2 to the n. Okay, and here we have this k. So this is the definition of quantum Fourier transform. It simply maps each computational basis J to its corresponding Fourier basis. So the Fourier basis here, you can think of the coefficients as the same as in the discrete Fourier transform. So it is just an e to the 2 pi I times this j and k over 2 to the n. Okay, so does this definition give you any intuition of why it can be written recursively? This, remember in the standard textbook of quantum computing, for example in the Zhicheng Zhang, this quantum Fourier transform can be implemented by a circuit, by a quantum circuit. And if you write out the quantum circuit description, then this description, if you consider it as a program, then the program text will scale up if you increase the number of qubits n. For example, for n equals to 100, then this program text is that large. But if we scale up n to be 1000, then this program text will become larger. So this is not a very economic description of the QFT. But using quantum recursive program, you can write out the program with a program text that is relatively independent of the number of qubits. So it describes a family of parametrized family of quantum Fourier transform. So I will just write out the quantum recursive version. So the idea is from the classical faster Fourier transform. In the classical, by this Cooley and Turkey faster Fourier transform, fast Fourier transform. So the idea is we can observe this QFT_n can be actually written as, can be actually defined by QFT_n minus 1. So the observation is, let's consider QFT. And we consider for different j, here we consider even and odd j. And that's using the first bit of j to represent whether it is odd or even. Or you can just think of, you are representing j as a bit string. So here, let's just use the first qubit to denote its last bit. So for example, if this one, sorry, here is the topmost bit of j. So yeah, it does not correspond to the even or odd of j, but it just represents the topmost bit of j. So you are just thinking of j as a bit string. So here we instead enumerate j from 0 to 2 to the n minus 1 minus 1. So you can consider two cases. First, it starts with 0 or it starts with j. So let's see how the mapping works. So if the first bit is j, then this state is proportional to, I just omit the constant factors. So here the summation k is still from 0 to the n minus 1. And sorry, L equals 0 minus 1 e to the minus 2 pi I j L over 2 to the n minus 1 2L. So we are considering even and odd k actually. So here this one is L equals to 0 to the n minus 1 times 1 e to the So we can, for j, just start with bit 0, then we can split the terms on the right-hand side into two groups. The first group with even k, and the second group has odd k. And similarly, we can also write out the mapping from one j to another. Here we have L minus. So here it's minus, and e to the 2 pi I j over 2n. Okay, great. So what's the observation is, I will use another color. These two parts can be actually obtained by QFT with n minus 1. So this, if you write it in this way, this one is just a QFT, and minus 1 apply to these. So you can write out these 2L and 2L minus 1 into the bit string, and it's roughly like this J. and you modify the first qubit. So let's rewrite these terms and say it becomes UFT n minus. I should find n is QFT n minus 1. You apply it to J, and you tensor it with square root. And this one is QFT and minus 1. You apply it to J, tensor it with this one. J, and 1. Okay. So now we have rewrite the definition of QFTN using QFTN minus 1. So this is a recursive definition, and yeah. So at this point, we can try to write it as a quantum recursive program. But here, what I'm saying here is an observation from the classical fast Fourier transform by Cooley and Turkey. Okay, so now write it here. Once we have this recursive definition, we can write it in this way. So QFT n it is just sorry, 2 steps. If m equal to n, we apply some S. I will define the unitary S later. So let's apply S to Qn. Else. So if m is equal to n, that means this part that does not exist. So we just apply some unitary, then prepare the second part. Otherwise, we need to condition on whether the first qubit is 0 or 1. So this is a qubit. QF Q M. If it is 0, then we apply the QFT n minus 1 on the second part. Otherwise, we sorry. The difference is this part, right? So I will just write out the whole program, and then tell you the intuition. So apply this. Another. So we write the whole program into 3 procedure declarations. So here we use these 3 procedures. And these 3 procedures are all recursively defined. So where is quantum recursion here? Here we have these quantum control flows. And in these 2 quantum branches, we call this procedure wrought itself recursively. So the whole idea is, first, before we go into the details, this program text is independent. Is program text, the length of this program text is independent on the number of qubits n. So that means no matter how large n is, you can always describe the QFT using this program. So that's one of the benefits of quantum recursive programming. You can always have an elegant and economic description once you know how to write it out in the quantum recursive programs. Okay, so why this program describe the QFT? So here, here let's just look at the main program QFT and n. So if m is equal to n, this is a simple case. We just have 1 qubit. So here I haven't defined S. S is just this matrix. This S is a elementary single qubit unitary gate. So S theta is 1 e to the pi theta minus e to the I pi theta. You can simply easily verify that if there is only 1 qubit, then its QFT, you can just use S0 to implement this qubit. So it's just a Harman gate. Okay, but for m, if m is not equal to n, that means we need to do some recursion. So first, these rows, what this rows do is prepare this part. So this is what the second procedure route does. So here we know that the phase in this state contains some information of I and j. So we need to collect this information. Sorry, not I, just the j. Here I is the one for the complex number. So we need to collect the information of j because j is a bit string. So here we are using this QF statement to read or recursively collect the information of j. So as you can see, we first check Qn. So Qn, here we start with some j, and we apply this QFT n, and it becomes this state. These are 2 cases by determined by the first bit of j. So we're checking the in from the lowest bits. If so, this is Q and n. So Qn just give you the last bit of j. So we just rotate these, construct this phase by these e to the 2 pi I j 1 over 2n times e to the 2 pi I j2 to the 2n. You just rotate using the information of each bit of j. So that's the rotation part. So the rotation part only prepares this state. And then is the recursion. So after you rotate, then you apply QFT n plus 1n. So this is just, there's some ambiguity in the notation, but what I want to say is here is n. This is a unit. Here QFT is a unitary, and here QFT is a procedure with two parameters. Here is n. Okay, n minus one. Sorry, n minus one. So you just recursively call the QFT n minus one, and in our parametrization we just call the n plus one n. Then we perform a shift operation. So the shift operation just so it's just to move the last qubit to the. You just do this. You just move the last qubit to the first qubit. So it can also be recursively defined using the swap gate. So that's the overall idea. You first write the QFT, the unitary, into using the recursively definition. Then you write it into a quantum recursive program. And the final program is its program text is independent of the number of qubits n. Is there any question about these examples?
So
yeah.
I probably don't totally understand. So when the rotate part, are the first qubit being rotated or the last qubit being rotated?
It's the last qubit being rotated. So I should say in this way. Minus one. Sorry. It should be. Oh, okay, sorry. It's the first qubit being rotated. Yeah. So you are just checking from n to m. So the checking is from. You start from m. This is the first qubit. This is the last qubit. So checking from this way. And finally, you will rotate this one because S is applied on Qn.
So it's like you first rotate the first few qubits, and for the rest qubit, the last rest qubits, you apply the QFT n plus 1 n, and then you shift them, swap them.
Yeah, you first rotate the first qubit, then you apply the QFT on this part, then you shift. You move the first qubit to the last qubit.
The question is, why don't you rotate the last few qubits and apply QFT to the first few qubits, and we do not need that shift anymore?
Good question. So the question is why we don't apply QFT to the first zero qubit, then rotate the last qubit without this shift. That's because if you write QFTJ in this way, the controlling the qubit you want to rotate. Sorry, I have to say in this way. So that's because you are you are conditioning in this qubit. So this conditioning on the first qubit, if it's 0, then it maps to the first state. If it is 1, then you map to this state. So actually, this qubit should correspond to this one. So so you need to first rotate it here. Then you do the rotation. Then I mean you need to. I don't know whether this is clear. So this J part corresponds to this part, right? So you are actually conditioning on the first qubit, and you do some rotation, and you move to the last part. Then that gives you the correct QFT. So you cannot do the QFT on this part because that's where J is held in the last n-1 qubit.
See. And another question is, what is the theta in the rotated?
You mean the theta? Oh, yeah. Great. Sorry, when I try to put the code into the whiteboard, I make a lot of typos. So here is the theta. Sorry, this should be 0. Here, this is theta. So theta is the angle of the rotation. Yeah. So it's just if you consider it in the procedure, it's just the parameters, the classical parameters. You do the rotation, and each time it should not be theta. Yeah, it's 0. Yeah. Okay. So the QFT in the QFT procedure, you call the rotate procedure with theta being 0. But during the rotation, each time when you create two quantum branch, the second branch will have a theta plus 1 over 2. So this theta will just, the effect of theta is actually gathering the information from J. So for different J, it will calculate this phase.
Oh, okay.
So that's what theta does. Theta just accumulates all the phase. So you rotate the first qubit step by step and accumulate this phase from J, information from J. And where does J? You are using this QF condition on the Qn. So Qn contains the information of J. So that's why we can write it in this way.
Oh, thank you very much.
Yeah, thank you for this question. Is there any other question about this example? Yeah, it's a slightly complicated example, as you can see. But once you write out the recursive definition, then the other part is rather intuitive. Okay. So let's move on to the next example. The next example is the fifth example of quantum random access memory. Or QRAM. So here, the QRAM I'm talking about here is the most general form of QRAM. So for those not very familiar with quantum computing, you can just think of it as a quantum version of the classical RAM. For classical RAM, you are taking some address, and so you have some register that specify the address you want to access. So here is the address register, and you also have a data register, which retrieves the information stored at the address. So you are using the address register to specify some location in this random access memory, and then this QRAM, it returns the data stored at that location. So this is the classical RAM. So what is QRAM? The most general form of QRAM, so you have different ways to quantize this RAM. One way is you can allow data to be quantum. The other way is you can allow address to be quantum. And the most general way is you can allow both address and data to be quantum state. They can be in the quantum state. So if we write out the QRAM operation, here I am just using a specific formulation of the QRAM. So we're considering the so-called swap QRAM. Because if you want to implement it in the quantum world, you need to make the operation unitary, so it is reversible. So, and by the non-cloning theory, you also cannot just copy, if this QRAM stores quantum data, you cannot just copy this data out, because due to the non-cloning theorem. So one way to define it correctly is you are not cloning this data out, but you swap it out. So it is still a unitary operation. So here, let's just define it precisely. So let's just assume the capital N is 2 to the n. It is a parameter. And what QRAM operation does, remember we also have an address register. And we have a memory. Okay, now let's just omit this data register. And what we do is we just swap this memory cell specified by this address register to the first location of this memory. So you can think of the first location in this memory served for this data register. So let's just write it out. For example, here the address is a bit string, say I, 1 to the n, and this is the address. Okay, we also have a memory. Memory is 0 to n minus 1. This is memory. Okay, so what does this uqrand does? It will swap the data located by this address register. This address register does not change, but you need to change this n. I will just remove the syntax here. And this one is n I. One and I minus 1 and 0 and I plus 1 and 1. So this is a unitary mapping. So what it does is you swap these two. So here I1n denotes I, which is I1n, which is I1 to IN. It's just a bit string that specifies the address you want to access. And here M is the data, an array of data stored in the memory. So it starts from M0 to M, for example, some Mi and M minus 1. So what we does by this uqrand, you just swap the data located by this or specified by this address with the first data in this memory. So you swap M0 and Mi. And this is a unitary operation, and of course it can be applied on a superposition state. So here actually what we are describing is you can allow the input state to be in a superposition, then you have some, for example, you have some amplitude, alpha I, and here you also have some alpha I. So that's the whole, that's what the uqrand does. This is a quantum random access memory. You are allowing the address register to be in a superposition state, and you also allow this memory to contain some quantum data. Is there any question about the definition of the qrand?
So what's the advantage of like putting the, like, for example, ith memory you want to the top?
Sorry?
So you're doing is like a swapping the ith memory you
Yeah,
want
yeah.
to the top. Well, what's the advantage of doing this?
Okay, great question. So the question is about why we are doing, you swap the MI to the first location. So I would say this is not an advantage. It's like mimicking the behavior of the classical RAN. So classical RAN, you will retrieve the information stored at the location I, then you to some data register, right? But in quantum, we can just move it to the first location. And this is equivalent that you have another, some data register. Let's say it starts with some initial state 0. And once you move MI to the first location, you can do another swap between MI and this data. I mean, it is equivalent to the following definition of qrand. I just want to make it simpler. So it is equivalent to I this is address, and 0, this is data. Okay, maybe this definition is slightly confusing, but it is equivalent to this one. So you just swap this 0 and the mi. So you just have this I, mi, and 0 to some 0. So 0 is at the position I. So they are equivalent. So this one you just swap mi out. And yeah, question.
So what's the dimension of the state vector?
Great question. So the question is about the dimension of this state. So here we define the capital N to the 2 to the n. So there are in total capital N number of memory cells in this memory. So if you want to specify the address of that many locations, you are actually using n bit, right? So this one, the dimension of this one, it has n qubits. The dimension of this one, it has n times some. It depends on how many qubits you use to store 1 mi. So you suppose this is just an array of qubits, then it's n qubits, capital N qubits, or it could be a qubit depending on how you define this qubit.
Okay, so the capital N is exponential of the lowercase n.
Yeah, you're right.
So would that be a very long dimensional state vector?
Yeah, that's a great question. So the question is, if we have this n and this capital N is exponential, then you need to use a lot of qubits to perform this QRAN operation. And that's why QRAN is still a controversial topic. But in some applications, we actually do not need to choose this capital N to be very large. For example, that means here the small n don't need to be large, so we can choose capital N to be like, for example, 1,000. Although this is already very large for the existing hardware, for example, if you only want to store a memory of 1,000 qubits, then this n is, you just take the log. So that means you can still have random access to 1,000 qubits. Yeah, right. So it does not mean we need this capital N to be super large, depending on the application you want to do. Does this answer your question? Yeah, but the question is a very great question. So if you want to do something like the classical, because in classical we have a very large RAM. If you want to do that exactly in the quantum case, then we must use a lot of qubits to do that. And at the current stage, the qubits are expensive, and we cannot afford for that price.
So if you use a capital N number of qubits,
yeah.
So this is just swapping qubit 0 and qubit I.
Yeah, specified by the address.
Okay.
So address can be in the superposition.
Okay.
So you might have, for example, you want 10 plus 100 something in the superposition state for the address, and you are doing some. So there will be entanglement between the address qubits and memory qubits. So there will be entanglement. Okay, so yeah, for such kind of UQRAN operation, how can we write it in the quantum recursive programs? Again, I will just I will just copy the program here and then explain it. So define this procedure, LRK, if k is smaller than n, then begin local and equals to n plus 2 So here is the quantum recursive programs for describing the UQRAN operation. So let's rename the quantum register. So here we name it QA, and its index is from L to R, right? L to anyway, and for the memory part, let's call it QD. So what does this program does? It splits a UQRAN operation that acts on the so here we consider the section starting from index from L to R in these memory locations. And so that's what L and R stand for. And the K stands for the depth of recursion. So you are doing K layers of recursion. And in each of the recursion, you are checking. So this is just how to find the index I. So using some kind of tree. So you are this is just using a tree to find the index. You are looking first. Okay. So if you want to do a QRAN, you will call this U 0 and minus 1, starting from layer 1. So first you look at QA 1. If it is 0, then it goes to left hand side. If it is 1, then you go to right hand side. Then you look at QA2. So you are just checking each bit of this address I. So this is the whole memory. If the first bit of I is 0, then it should fall in the left part of this memory. If the first bit of I is 1, then it should fall in the right part of this memory. Right? So this is just how you using address to find the location in the classical way. But in quantum case, we need to use a QID. And that's the only observation we need to make. So you just check each qubit of this address register using the quantum if statement. If it is 0, then you go to the left-hand side part. So you just go to the LM, where M is the middle point. So this is L, this is R, this is M. So if the first qubit is in state 0, then you go to the left-hand side part. Otherwise, you go to the right-hand side part. And remember, our operation is swapping the data specified by this location to the first part. So if it's on the left-hand side, you just swap this one to the L, and we are done. But if it is on the right-hand side part, you are actually swapping this to N. So we need to do some additional operation to swap it to this part to L. So we can always keep the swapping to the first elements to the first location. So that's why here we have this swap. Yeah.
Question.
Sure.
So this program, it eventually does not goes into the one you wrote here, because like you have many intermediate swap. So for example, your I is going to intermediate with the first L and it goes to there, and the other goes to there, the other goes to there. So there are a lot of changes in locations of others unrelated memories.
Yeah, you're right. So yeah, you are saying we have a lot of swap. Yeah, you're right, because that's all because you are doing some random access, but you need to first find where the location that specify I is. So during the finding, you are going from both directions. Yeah, and yeah, you're right. Here we are doing a lot of swap, and if you try to optimize this operation, you can actually do much lesser swap than this program. Yeah, you're right. So maybe you can design some quantum circuit, that's some kind of low-level quantum circuit that does less swap operation than this program does.
The thing is, I mean, so if you're doing a lot of swap for unrelated like memories in this program, then for the next time you want to get out some memories, it might not be the correct memory you want, right?
Could you repeat your question again?
So like your memory, you have an every address is mapped with some memories,
yeah.
And you swap them. So each address is swapped to a different memory before you swap. In this case, when you get the first address, you get the first memory, and then you get the second address. So everything gets swapped. How do you guarantee you still get the correct memory you want?
Okay, that's a great question, and this question is actually about how QRAM works. So in QRAM, here we can allow this address register to be in a superposition. So for example, it can be 1 plus 8, for example. Let's just consider it contains two memory locations. So that means if the address register is in state kit 1, then you are swapping the first, let's just take 2. So you are just swapping the second data with the first data. And if it's in state 8, then you swap the 8th data with the first data. So that seems to be totally mess up this memory, because you with different address you are messing up the memory there. And yeah, and this is inevitable. That means because this address register is entangled with this memory, this whole memory. But if you just look at, hey, if we just look at the address 2, if the address register is just in state 2, then this memory is, I mean, it is just like the classical, so it's normal. But if you look at the whole quantum state, that contains an entanglement between the address register and the data and the memory register, then it seems to be something messed up. So that's why when we are using the QRAM, we need to be careful. If you carefully use this QRAM, for example, for example, if you use some algorithms that work like this, for example, you are, there are some early algorithms on quantum works like the 3, 4 element distinctness problem. So they use some ideas of you are doing some superposition of classical data structures. So for a classical data structure, you need to store it. And if you want to access the data in this data structure, you need to store this data structure into the QRAM. But if you use this QRAM correctly, for example, you are using this I, this is M, and they are entangled. If your algorithm, it is work like you are conditioned on I and doing some UI to M. I mean, if for example a unitary, it just maps I, M. Here actually M is, it will depend on I. If the unitary just do such mapping, then it won't be incorrect, because here actually we are looking at when each I is in the computational basis, then we do some operation depending on I. So you won't mess up the memory, because it's just like the quantum if statement. You are looking at this I when it is in the computational basis. You do some UI depending on I.
So you're not swapping here?
No. I mean, let me think how to make this. So for example, this state, this alpha I am I, this state is after you have do some swapping, do some QRAM access. Then you want to, for example, so this I represents I should say in this way. So for each I, for example, you are storing some classical data structures. Let's just say you store a binary tree into this QRAM, right? You are storing this binary tree into this QRAM, and you want to access this binary tree in a classical way. So you are saying, okay, for I is equal to 10, this binary tree might be some structure. If I is equal to 11, this binary tree has some structure. But when you fix some I in the computational basis, the memory is always the binary tree. It does not. It's not a superposition of something else. So once you fix this I, this memory is it's actually classical in their algorithms. But of course, in general, M can be in the even if you fix I, the second part can still be in the superposition in the quantum state.
My question is probably not a superposition. It's not like when you're swapping things. So for example, if your I equals to 5, which is like 101, so that's probably considered like the basis of just 101. So then in your algorithm, your M5 needs to swap with M4. Am I correct? Or probably M2, M1, and M0. In this case, like your eventually order would not be like 5, 1, 2, 3, 4, 6, but it's like your 5 and 4. So the fourth should be the fifth, and the second should be the fourth. First should be the second. 0 should be like this kind of things. It's not like the one you wrote here, which is just a single swap with 0 and I. And I suppose if like with a lot of leaps and swaps, the whole memory is messed up.
Wait.
Am I understanding correct?
Can you write something here? It's slightly technical. I mean, can you explain what your question is? Or yeah.
Right. So let me try to describe it again.
Sure.
So, what I heard from your introduction of this algorithm is like for every layer, you are swapping like the I or like the current with the left most in your part.
You're right.
And you see, every time you get a 1, you put the L into the AND, which is mostly a binary search.
Yeah.
So which is like you are swapping things. So for example, in this case, in the 101, you probably swap 5 with 4. I probably need a more careful calculation to give a correct concrete example, but.
Yeah. So maybe let me just explain this program again. So if you go into the left-hand side, you just that means this data is on the left-hand side, right? So you just swap these data with the left, and you are done because our goal is just to swap some data with the leftmost elements. But the problem is when you go into the right-hand side, now you are into the deeper layer of recursion, right? So the L now is N. So what this program does is you swap this element with the first element here. Now it's not correct because for the whole L and R, it is in the middle. So we need to fix this. So let's swap this one with this one again. So now this element comes to here, right? But there's still one thing not correct because this element comes to here because you do a swap. So now we need to make this element back. So we need to do another UN plus 1 or K plus 1.
I see.
Yeah. So finally, in both cases, you always swap this one and this one.
Okay.
Yeah.
Okay, thank you.
Yeah.
How hard it is to implement the QF? I mean, in real common stuff.
Yeah, great question. So the question is about how to implement QIFT, and that's what I'm going to talk about. So we need to use an architecture called quantum register machine, and then we compile this program into some low-level instructions, then run this instruction on that quantum register machine. And that's a great question, and I'm going to talk about this. So let's just start this part. So let's skip the last example, and I think I can start to talk about the implementation part. So I will write your question here. How to, I guess what you are actually asking is how to efficiently implement this QIF. Or more general, we want to implement quantum recursion. The quantum recursion also contains a procedure call. So intuitively, for example, in this example, if you straightforwardly implement this quantum if statement, it contains 2 control unitary, right? So for example, here, we might write it in such circuit, for example, 0. Then you do the first branch, whatever. Let's just call it U0. And if it's kit 1, then we do this control U1. So that's a straightforward way to implement a quantum if statement, right? But the problem with such implementation is you are doing two branches sequentially. But our intuition about the quantum control flow is here we have Q. It will guide the control flow into 2 quantum branches. and we are going into two branches in superposition. So why there's a difference between this one and this one? Maybe we are the problem is here we are thinking about this one. I mean, if we have some machine that can be in the superposition state, for example, it's like a classical CPU. So let's remember how a classical CPU works. So classical CPU, you have this RAN, you have this classical CPU, and each time you will have some register PC that points to some part of the RAN, and you read the instructions. So here, this RAN store the compiled program. So for example, this is your original whatever C++ or Python program. You compile it into some instructions. And you store this instruction into the RAM. Then you use the CPU. What CPU does, it repeated operations in each instruction cycle, and at each instruction cycle, it's first fetch the instruction from the QRAM. So the QRAM will return some instructions. Okay, if this, then we decode. Here we have this fetch, decode, execute, branch, or something. So for example, if this instruction is A, you add some register A by 1, it can be some instruction like this, or it can be a branch instruction you jump to, for example, branch to another position. So each time you just fetch these instructions specified by this PC, then you decode this instruction, then you execute this instruction. And if this instruction is branching instruction, you might change PC. For example, it jumped to another place. So you update this PC. So that's how classical CPU works. Right? If we want to support quantum control flows, because a classical CPU, you will have these two branches, right? So your compiled program might contains two parts. The first corresponds to the first branch, and the second corresponds to the second branch. And your PC first put the program counter here. So here PC stands for the program counter. The program counter first come to here, and you see, okay, this is a if statement. So if the condition is 1, we just go through this first branch. These are the code for the first branch. Otherwise, I would jump to here. We skip the first branch and we execute the second branch. So that's how a classical CPU executes some kind of if then else statement. But now we have these quantum control flows, and if our CPU, it can be in the superposition state. At this point, let's just imagine if your CPU can be in superposition state, then this PC can be also in the superposition state. So you are having this PC to be alpha, some PC0 plus beta PC1. So you are accessing. So now this becomes a QRAN. You are accessing this QRAN using a superposition of address, and you read all these instructions. They are also in superposition. In this way, you can execute these two quantum branches in superposition. And that means, so if you look at this sequential implementation, if you calculate the depth of this circuit, it will be T0 plus, it will be proportional to T0 plus T1, because you first execute U0, for example, its execution time let's assume it to be T0. then you execute this U1, let's assume its execution time to be T1, then the depth of this quantum circuit will be T0 plus T1. But if you can implement two quantum branch in superposition, then this time the depth of this execution will be max of T0 and T1.
Quick question. So
Sure.
is it just from the efficiency perspective? So for example, if you just implement it as the one on the left, is it still the correct execution?
Yeah,
Okay, thank you.
you're right. So here we are just focusing on how to efficient implement these quantum control flows. And when you think of quantum control flows, you are actually thinking about, okay, we try to execute these two quantum branch in superposition. So why we need to execute the first branch then the second branch? We can execute them together in superposition. So that's a natural intuition for how you execute the quantum control flows. But to actually implement such intuition, you need to design, okay, how to compile this program, how to make an architecture that supports such superposition of your CPU. So that's what I'm going to talk in the remaining, so we have roughly 10 minutes, then in the next lecture I will talk about the implementation. Does this answer your question?
Your instruction, like in the CPU, the instruction stored in RAM. So, but here in the QF control flow, you don't store the instruction in QRAM.
We will store the instruction into the QRAM. So that depends on how you implement this program. So we need to design how you store this program, how to design the CPU, and how to design this compilation such that, okay, let's just run this compile program on this architecture and it will go into the quantum branch in superposition. So that's our target to design. Yeah, and here, although this is just T0 plus T1, this is just the max. Once you have the recursion, actually here we are generating a tree, right? In this example, we are generating actually this is not quite a good example for why we focus on the depth of the implementation, because here we are using the QRAM as an example, and our implementation will rely on QRAM. But whatever, this example, it can illustrate when you combine the quantum control flows and recursive procedural calls, their interplay will become complicated, because if you have recursion, you can generate a tree using, here K is the depth of the layer. So for example, if you go into depth K, the number of quantum branches generated in this tree is 2 to the K. So you have 2 to the exponential number of quantum branches you need to go. So if you using this sequential implementation, then its time will be 2 to the K, proportional to 2 to the K, right? Because you are going into each of the branch sequentially. You first apply this subtree, then apply this subtree, so you take the sum of this tree and this tree. And in each of these three, again, you are taking the sum. So if you sum all them up, it will be proportional to an exponential to the number of branches. But if you take the max, then this will be max of, let's say, each of the branch T1, T2, to T to the 2 to the K. So this will be the sum, T, will be the sum over x equals to 0 to 2 to the K minus 1, Tx. It's proportional, roughly. And if you can go into 2 quantum branches in superposition, then these should be proportional to the max of x over x equals to 0 to the k minus
you can put your instructions in the Q RAM, that's cool. Is that true?
Sorry?
I mean, is it true that you can put your instruction in the Q RAM?
Yeah, it is true. Actually, QRAM, you can initialize this QRAM into some quantum state, right? So we can just initialize this QRAM by some in some computational basis, and this computational basis represent the program.
Yeah, so you're gonna have to decode the instruction, right?
Yeah.
So that would require QF by
If you want to decode, yes, you can write that QF. You can write it as a QF, but at the architecture level, we will describe everything by the quantum circuit. So to implement such architecture, we will actually design the complicated quantum circuit to describe how you execute this on this architecture.
Okay.
Yeah. Okay, let's just 5 minutes. I will just talk about how give you some intuition of how we can do this. Okay, we have already seen how quantum recursive program can benefit the convenience of describing quantum algorithms. And now we are going to talk about the second part, that's how to efficiently implement such quantum recursive program. So remember in the first lecture, we have mentioned that programming languages is the bridge between the human and the machine. So in the last several lectures, we have already talked about this part. That the programming languages provide a convenient way to describe quantum algorithms. It provides a high-level way. You don't need to design. If we are talking about the high-level programming languages, it provides a high-level way. You don't need to concern about the low-level quantum circuit. You just describe your algorithms in these high-level languages. And we have introduced the quantum recursion, which includes quantum control flows and recursive procedure calls. So you can use these two programming features to have more expressive power to describe your algorithms. Now the second part is once you have written such program, how you can implement that program. So just like in the classical world, we would like the machine to automatically do this. So the machine will help you, a compiler will help you to compile this high-level program. You compile it into some low-level programs. In general, you can do it describe it as program, but here actually we are doing this program consists of instructions. So we compile it into low-level instructions, and this compilation might consist of many levels. For example, and finally we might want to compile it into some quantum circuit. Okay. So that's the part we are going to talk about. Now, I will draw the so for RQC++, that's our source program. RQC++, that's our source. We designed so this work is this one called quantum register machine for efficiently implement quantum recursive program. So we designed a quantum instruction set called QINS. This is an instruction. QINS is an instruction set, just like the classical instructions. And these instructions, we need to use an architecture to implement a program composed of these instructions. So first we have a compilation process that converts a source program in the RQC++ into some low-level instructions. Then we will feed these low-level instructions into an architecture called quantum register machine, and we will do two things. First, we need to perform some partial evaluations. This partial evaluation is used to gather the quantum control flow information. So we have some quantum control flow information. So this quantum control flow information, they will be used to aid the execution of these low-level programs. So here we just gather the compiled program and this quantum control flow information for the execution. And this part is just quantum register machine. Okay, and finally, using this whole implementation, actually we can obtain some bonus. This bonus is, it provides some, for certain subroutine. We can have an automatic parallelization. So as we mentioned before, if you can implement quantum control flows, if you can go into quantum branches in superposition, then actually you are doing some parallelization instead of you straightforwardly implement two branches sequentially, right? You are actually doing, so let's remember that diagram. If you're doing this sequentially, then the depth is not good. When you have exponential branches, the depth will also go exponentially. But if you can go into two quantum branches in superposition, then the depth is only depends on the maximum of this quantum branch. So actually you are doing something like a parallelization. So that's the overall picture for the implementation. And I think the time is up, so maybe I will just leave this part to the next lecture. Thank you again for attending today's lecture. Is there any question or comments?
How many lectures do you have left?
One, just
One
one.
more?
Yeah. So maybe we don't have much time to get into every details, but I hope the next lecture will be, I mean, you can get some feel the idea is beautiful because you are actually allowing, I mean, you are designing a whole system and you are allowing the CPU to be in the superposition state, and that can goes into quantum branches in the superposition. Yeah.
You are talking about the superposition state of CPU or like quantum working quantum flow, like working flow, like
Quantum control flow.
control flow. Yeah. Quantum control flow. I'm very curious. Like seems like quantum control flow is just put the controller in a superposition. However, it actually can do some like classical execution in the real leaf node, like in the execution parts, right? For example, I can use quantum control flow to control different like classical computing resources to do some classical computing. Is that?
Okay, that's a good question. So the question is whether we can use quantum control flows, and in each of the quantum branch we do some classical thing,
Yeah,
Right.
okay.
So actually, yeah, so the answer should be yes and no. The yes is since the classical part are still quantum parts, so you can make the whole execution as a large unitary. So if you have two quantum branches, then you do C0 and C1, and C0 and C1 they are mimicking some classical behavior. Now of course they can be written in the quantum recursive program. So yes, we can use a large unitary to describe it. But the caveat is, here we are describing a unitary. So we do not allow these C0 and C1 to contain some measurements. So that means the image of maybe the classical computation you are thinking about
Cannot be measured.
cannot be do it in this way, but classical computation can always be converted into quantum computation by introducing some garbage data. So yeah, so you can do it in this way, but not that way. You cannot just combine two classical computation in superposition, because that's not a unitary. Yeah.
Thank you.
Thank you for this question. Are there any other questions?
So I'm curious, are you going to implement a stack in the QRAM to do the recursion?
That's a great question. The answer is yes. We're going to, the question is, in classical recursion, we will use a stack to implement the recursion. And now in quantum recursion, actually, we have this QRAM, and we will split QRAM into many sections. For example, this is one for storing the program, so that when you compile this program into QINS, you will put this QINS instruction into the program section. We also have these variable sections. So variable section will store the value of quantum variables. For example, you have Q1, Q2, these are quantum variables. Their value will be stored in this part. And here are some other parts for the execution. We also have a stack here. So this stack part is like the classical stack, but it can be in the superposition state. So for the CPU part, we have a list of registers. For example, you have this program counter, this stack pointer. The program counter will point to one location in the program section. And the stack pointer will point to the top of the stack. And these two can also be in superposition. And there are some other registers for the execution. For example, we have an instruction register, and this instruction register just stores you fetch the instruction at PC, so you fetch the instruction into this instruction register. So it's like the classical CPU work, how it works, but the overall point is you need to make this implementation unitary for it to be on in a quantum computer. So one property you need to keep in this implementation is everything is reversible. So that means we also need to borrow some idea from classical reversible computing. And reversible is not enough because quantum control flows include the quantum state. So we need to also design some other structures that supports these quantum variables. So you need to make these quantum control flows and recursive procedure call. You need to make them work harmoniously. Yeah. Does this answer your questions? Yeah, great. That's a great question. And actually, we are going to get into some of the details in next lectures.
Great, thank you.
Great.